We've covered the Vesper theory and Lewis theory. And of course, the Lewis model is an oversimplification, right? There we're showing electrons as little dots located around specific atoms. When we learned back in I think it was chapter 8, that electrons are waves and particles at the same time, and they're very mysterious and hard to understand. So the Lewis model has its uses because it is simpler than the other models, but then it also doesn't apply in as many to as many different situations. So there are more advanced bonding theories, and these are going to apply quantum mechanics. So there are quantitative approaches that can be used to accurately predict a lot of different things: bond length, molecular geometries, dipole moments, and those involve a lot of math and some pretty hairy math I would not want to look at. So what we're going to do is we're going to look at two of those theories, but in a qualitative manner, meaning we're not going to get into all the math involved in that. We're just going to look at the concepts, the ideas of them. So first we'll talk about valence bond theory. Valence bond theory is a theory that treats a chemical bond as being the overlap between orbitals on different atoms. So we learned that electrons reside in quantum mechanical orbitals that are localized on individual atoms. And so those are s, p, d, and f atomic orbitals. But when two different atoms come together and form a bond, those standard atomic orbitals can be blended or sort of averaged together, and they can be changed. And so these are called hybridized atomic orbitals. So when we have two atoms approaching each other, we've got interactions between the electrons and nucleus of one atom and the electrons in the nucleus of the other atom. And so in valence bond theory, we're looking at energy changes as a result of those interactions. If the energy of the system is lowered by the interactions, then a bond will form. If it is not lowered, then a bond will not form. Nature is always tending towards lower energy, like balls always roll down the hill, they never roll up the hill on their own. So in this graph, we're looking at energy on the y-axis, so higher energy at the top and lower energy at the bottom, as a function of the distance between two hydrogen atoms. So if we think about taking two hydrogen atoms and bringing them closer to each other. So here they're a certain distance apart, and this is causing the energy to be lowered a little bit. There's an attraction between these. As we get closer, the energy lowers even more. The orbitals of those electrons are starting to overlap. And here it's going to overlap and lower the energy even more. And then as we get closer, now, this is like, a close talker, right? That person that stands too close and talks to you, right? And it's just like you want to back up. You're too close, right? But if they're far away, you can't hear them, and then you're kind of drawn in. And so there's this distance, right, where most people feel comfortable talking to each other. So that's kind of like this sweet spot here. If the atoms get too close, then they're repelled from each other, right? So there's this place where the energy is at a minimum. And if we look at that distance, that corresponds to the energy of the bond and the distance, the length of the bond, right? Any questions about that? Does that make sense? You have these two things and they're attracted to each other, that pulls them closer together, but if they get too close, then they're repelled. Right? So there's a sweet spot. So that interaction is going to be stabilizing and negative when those atomic orbitals contain a total of 2 electrons that can spin pair. So we learned when we were doing orbital diagrams for an individual atom that if you have two electrons in the same orbital, one will have spin, a positive spin, and one will have a negative spin. And in the analogy, this was people sleeping one right side up and one upside down in the bed, right? And it works out better that way. So in these bonds, typically what will happen is that the electrons involved here will come from two half-filled orbitals. So on one atom, you have a half-filled orbital with one electron in it. On the other atom, you have another half-filled orbital. It's got one electron. And as those orbitals overlap, now those two electrons can change their spin, just like you can decide to get into the bed right side up or upside down. And so what happens when those two electrons and those two orbitals overlap is they will spin pair. One will be positive and one will be negative. So usually we see this happening with two half-filled orbitals, but it's also possible that we can have two electrons from a filled orbital on one atom overlapping with an empty orbital on another atom. This is called a coordinate covalent bond, and we'll talk more about that in Chem 1b. So when two atoms with half-filled orbitals approach, those orbitals are going to overlap and the electrons align with opposite spins. Any questions? So this is a summary of valence bond theory. So valence electrons in a molecule are going to be in quantum mechanical orbitals. Chemical bonds arise from the overlap of half-filled orbitals with spin pairing of the electrons. And then the geometry of those overlapping orbitals is going to determine the shape of the molecule. So let's look at how this might work. So let's look at a bond between sulfur and hydrogen. So here we have sulfur, and we're looking at the valence electrons, because those are the ones on the outside that are going to interact with other things. So here's the orbital diagram for sulfur. Sulfur has two half-filled orbitals in that 3p sublevel. So each of these could possibly overlap with the half-filled orbital on hydrogen, right? So we could have those two overlap, and then sulfur has this other half-filled orbital that could overlap with another hydrogen. So here we've drawn those orbitals. So the vertical here is the filled p orbital. That is that lone pair, this first one here. And there's three p orbitals, and they're at right angles to each other, right? So here's one that's perpendicular to that one, and then here's the other one. So one of these electrons is from the sulfur, and in here one of the electrons is from the sulfur. And then it's overlapping with the s orbital from hydrogen, which is bringing the other electron. Does that make sense? Are these two half-filled orbitals, and they're going to overlap with each other. And in that orbital overlap, you have a pair of electrons. So what this predicts, because we know what the orientation of these p orbitals is, they're at 90 degrees relative to each other. And so looking at it this way, we would predict that the bond angle here would be 90 degrees, right? And if we measure the actual bond angle, it's 92 degrees, which is pretty close to 90, so that's not too concerning. But if we look at Vesper theory for this molecule, where we're looking at the Lewis diagram, Vesper theory looks at this and says, well, that sulfur has 4 electron groups around it, right? It has these single bonds, those are each one group, and lone pairs are each one group. We've got 4 groups, and how do 4 things spread out and get away from each other? They're going to form a tetrahedron, right? And so Vesper theory is going to predict 109.5 degree angles But because of these lone pairs, which take up a little more space, the angle between the hydrogens is expected to be a little less, right? So here, this is not matching up with valence bond theory, but valence bond theory seems to be matching up pretty okay with the actual bond angle. Conceptual question. So if you ask what is a chemical bond, there's multiple answers to that question. It's going to depend on what bonding model you're looking at. So this is asking us, according to valence bond theory, what is a chemical bond? Is it a lone electron pair? Is it the overlap between half-filled atomic orbitals on two atoms? Is it the overlap between filled atomic orbitals on two atoms? Or is it a shared electron pair between two atoms? What do you think? I think it's B. What we're talking about here is half-filled atomic orbitals. When they overlap, that's where you get the pair. But if you have two filled atomic orbitals, they're already full, and so they're not going to be able to overlap. Okay? So this one just doesn't work out at all. A lone electron pair, that doesn't make sense because that's off on the side, and it's not connecting two atoms together, so that's not a bond. This is a definition of a chemical bond, but what theory does that go with? Lewis theory, right? Lewis dot figures where we're looking at a shared electron pair between the atoms as representing a bond. Any questions? This is not the sort of a question that I would ask on an exam, just so you know.